So this is a talk that sort of is focusing at one particular interesting thing that I came across when I was working on one project. And I'll start a little bit by talking about the sort of motivation for this and why am I actually doing this, and then I'll show you some things which should be hopefully fun from the sort of functional programming side. I'll be using F# and I'll be using a project that compiles F# to JavaScript because it's 21st century, right? And my name is Tomas Petricek, and I recently started at University of Kent in the UK, but I'm still occasionally doing some work as part of F# Works, which does various sort of F# trainings and consulting. So when I started this project, I started thinking about the project maybe 4 years ago. This was funny. Now it's not funny anymore. But it got a lot easier to explain what I'm working on, because there's this buzzword called post-fact, and the sort of idea is that it's sort of harder and harder to talk about factual information. And as someone who's sort of interested in programming, I always thought, well, we should make programming with facts at least a bit easier, so that those who actually care about facts at least can access them relatively easily. So the motivation for the project was to make it really, really easy to produce some simple data analyses that people like journalists might use if they want to refer to some facts from various open sort of government databases and public data sources and so on. So I think one really interesting trend that you can sometimes see in the media is this sort of rise of digital or data journalism, where journalists are creating more and more of sort of various data-based, data-driven stories. And I think this is just a beautiful example of it, because it tells you just so much with this one little picture. So this is a history of the Olympic Games from sort of 1896, and it plots the number of medals awarded to different countries, and you can just look at it and you'll see immediately that there's these two gaps, which is the world wars. So you sort of see the history of 20th century in just this one picture. The other interesting historical fact is here. So that's where first the US didn't go or boycotted the Olympics that were in Moscow, and then the Soviets did the other thing the next year, and you can just see it in this little graph. But equally, so this is New York Times, who's probably the only media company that can actually produce this, because it's really hard. You have to know all the different technologies from like Python to D3. You have to probably write your own rendering for this to actually make it this pretty. And there's a lot of problems with this. So can you reproduce it? Well, sometimes they give you source code, and if you're really lucky, then you will be able to run it. Can you check if the visualization is misleading? Well, even in this simple thing, you could count medals going to football, or as they call it here, soccer, as like, I don't know how many players is there. It's even those who don't actually play get the medals, so you get like 20 medals, and it can skew your chart quite badly. Can the reader explore further? Well, you can't even sort of say, I just want to look at maybe running medals, because they just give you this picture. So the project that sort of motivated this, that I've been working on, is trying to make this sort of simple data visualization, this simple data aggregation easier. It's called the Gamma. If you search for it, you can find the website and play with it. But what I want to talk about is sort of one particular aspect of this. So when I was doing this, I was like, well, what should a sort of really simple programming language for doing this sort of simple data science look like? And there's a really nice talk by Jonathan Edwards, who does work on sort of usable human-centric programming languages or programming environments. And he has this chart as just the illustration, so there's no labels for the axes. I apologize. And what this tries to say is that sort of there's this, like how complex it is to produce a thing. That's one axis, and the other is how many people can do it. And there's plenty of things that are relatively easy and lots of people can do it with spreadsheets. There's sort of things that are difficult that you can still do with spreadsheets. And then there's this gap where you can't quite do it with spreadsheets, but if you want to solve it by using a programming language, it will suddenly sort of jump all the way here where it's actually quite hard. So even programming languages like Python, you still have to learn quite a lot, and it makes your problem complicated, even if you actually sort of didn't want to do something that sophisticated. So there's spreadsheets, there's Python, there's Haskell right here. And I think that the sort of interesting problem is what can we put somewhere here in the gap. So I'm not saying I've done this. I think there's still plenty of room for investigation, but maybe what I've done is something like sort of get here. So the scale is non-linear, and actually I'm somewhere here. But the motivation is sort of, can we do something that will be more that will let you solve more complicated things than Excel, but be a bit easier than, say, Python. And I think there's lots of things we can learn from things like spreadsheets. So I think sort of lots of people at this conference, when we look for inspiration, we looked at mathematics and at all the beautiful abstractions that category theory provides. But that's still in that graph, remember, somewhere here. So what is there in spreadsheets that's so nice? And one thing I find really, really nice about spreadsheets, so look at me using Excel. This is a nice animation. When you're doing something like this, you're actually always working with concrete values. There's some sort of variable to refer to the cell, but really you do it by clicking, and you're always working with concrete values that you see, and then when you drag down, it's not like you have to write a function that takes some sort of symbolic variable A and B and adds or multiplies them. You actually just do things with numbers and then apply it across. And you could model it as a function, that's fine, but that's not how you do it. So this way of sort of working against concrete data, I think that's a really powerful idea. And the way it works here is that you do something with concrete data and then you extend it to make it work on sort of larger number of things. So can we create a programming sort of environment that will let you write code, because code is good, code is reproducible, you can analyze it, you can modify it, but give you more of a spreadsheet-like experience. So this is the project that I've been working on, and I'll show you a little example. So I've been sort of using that New York Times article as an inspiration, and I've got the data set with Olympic medals ever awarded. You can sort of scroll through this. This just gives you a preview of the first, I don't know, 10 or 20. There's what year is it, what's the team, and what medal it is. And the idea is that I can do basic data aggregations here, and this takes, it's a little scripting language that runs in browser. That's what the Gamma project does. But it takes a lot of ideas from F#, where we have these nice type providers, where you sort of type dot, and on the fly, the type provider generates what you can do next. But here, I'm using that sort of trick for doing data aggregation. So what I can say is, choose one of these operations and say group data, and then it says, well, what do you want to use as your grouping key? So what do I want to do? I'll create a little chart that shows you the number of different teams competing in Olympics over time. So presumably it will be sort of fewer teams at the beginning, more teams at the end. So I want to group this by year, and I can see preview. I've got one sort of row per 1 year, and then I can add another key, or I can select various aggregation operations, such as I can count the distinct number of teams. And this is definitely sort of giving you just a fixed set of operations. So you can't do anything, but you can do lots of things, and that's the point. So then I've got a number, I've got the year and the number of teams in the year, and just to make sure, I'll sort this by year, and you can see I've got a preview that shows me what my data looks like after applying the operation. So I actually want to sort it the other way around. So I'll do this, and then I can say, give me a data series or time series where the key is the year and the value is the number of teams. So I've created a time series, and then I can say, give me a line chart with this time series, and here's my, let's see, smaller. Here's my time series chart, and it doesn't look all that great, so I can change a few arguments here. All right, this is not perfect. 1896, I think I need. And I'll set title as well. It's kind of annoying that the browser keeps jumping. Right, so this is the number of teams competing in Olympics over time. And you can see when it started, I guess like half of those teams that appeared are the British Empire falling apart. But don't tell them. So as I was doing this, there's a few important things. The most important thing is that as I was sort of typing the text, for example, the preview updated instantly. And the way how to do this is the interesting problem. In this case, actually sort of the data isn't too big, so you could conceivably just rerun the whole program and get the chart. But if you ended up doing anything a bit more complicated or using a bit bigger data set, that just wouldn't work. So the nice thing that I'm doing here, and that's what I want to show you, is how to do the sort of live interpreter for this language, where if you make an edit, it will only recompute the bits that have actually changed. So in this case, when I edit the title, aside from my browser jumping around, which is not my problem, the key thing is that the first few lines that do the aggregation, they don't get recomputed. So that's something that happens just once, and then I edit my program, and as long as I don't change the structure of my aggregations, that bit doesn't get recomputed, and I just render a different pretty chart. So how do you do that? So I'll sort of split the talk into two parts. First part is how not to do it, and the second part is how to do it. So the how not to do it part is, if you buy a textbook on writing compilers, then all those compilers are built for the computers that you can see in this building. Well, actually, maybe not. They were built for the big ones, where one computer would take the whole building. The basic programming you can do in one of the rooms is actually way more advanced than this. But the idea for these sort of old-fashioned compilers is that you bring in your punch cards, you feed them to the compiler, it loads them and spits out your compiled program. So it's batch-based. You take your code, produce compiled code. Or you take your code and produce result if you're just evaluating. The way textbook compilers do it is that they parse your code into a syntax tree, then they walk over the syntax tree a couple of times to do type checking, evaluation, and then produce results. Or, more likely, if you give them program that's not right, it will say error, as you saw in the previous talk. It might give you a better error message, but it just says, I can't do this, that's the wrong program. And none of these really are good for what I was showing you, because I need to have something that runs in the background. I'll talk about the internals, and I also need something that when you give it a bad program, it will say, well, I sort of think you mean this, and I'll run it. So when I'm showing the demo, if I gave it a wrong program, it would still sort of run it, despite the fact that some bits of it were not correct. But textbook compilers are a good start, so we'll start with that. And what I'm going to work with is this little programming language where you have let bindings, and you have member calls, and you have a bunch of constants. And I have a little library for doing things with images. So you can load two pictures, then you can grayscale one, blur it, and combine them. It's an expression-based language, so this is just an expression that evaluates this after doing some variable bindings. Right, so how do we work with something like this? So the way normal compilers work is that they will take your code, so this is my sample code, and first of all, I'll build a tree that represents this parsed code. So overall, this is a let binding, where the thing that I'm sort of calculating as a value of p, to do that I need to call load, and I'm calling load on this sort of global variable called image, which is some object. I'm giving it pope as an argument, so this is a string. And then when I do this, I'll call blur, and the instance of this will be p, and the argument will be 5. So I've done my parsing. I have a tree, and then what normal compilers or interpreters do is that they walk over the tree. So I could have one pass that does type checking, and it will say this thing is some sort of image constructor. This is a string. When I call load, I get back an image. And then I know value of p, because this is what's assigned there. So this is going to be image, that's type. This is a number, or int. I do blur, I get another image. And then my overall result of this is an image. So I've done my type checking over the tree. And because here I actually want to run things, I could run it as well. So I'll say this, well, it's just some sort of object that doesn't really mean anything. It's just a thing for loading stuff. This I evaluate as a string, so this is pope. When I load it, I get an image of a pope. This is a pope. Popes have fancy hats. Then the value of p is, again, this pope, because we just did him over there. Value of 5 is 5. Then we blur a pope. This is a bit where it gets tricky. This is a blurry pope. And then my overall result will be blurry pope. Right. So this is how normal sort of interpreters and type checkers work. And I'm going to show you a couple of bits of code for this. So in my programming language, I've got this type representing expressions. I think many of you have seen something like this or written something like this already. So I have let bindings, variables, member accesses, calls, constant and binary operations. The only sort of tricky thing I'll talk about later is that everything here is wrapped in this node element. So like all the stuff here on the right is wrapped in node. And this lets me add some annotation to the nodes in the syntax tree. And you could use this to store things like location, where it's in the file. And I've got an evaluator. And in my evaluator, I've got a recursive function that does pattern matching. And for numbers and strings, it just returns a number and string. For variables, it does lookup in some sort of dictionary that it keeps with all the variables in scope. And I've already implemented binary operators, so I can do various calculations. I've got a bunch of these things unimplemented with the lovely null operator. And I'm running this using Fable, which is F#, the JavaScript compiler, and that's running right here in the background. And when I make a code change, it will reload. So this is really a fantastic way of playing with F# because you just run some magic commands that they give you on the website, and you get a beautiful template where you just say yarn, and it will keep compiling your code in the background, and you can write code and see what's happening. So this already can do 1 + 2. It can maybe even do brackets. And it reports some diagnostics that we'll look at later on. But if I do image.load, then that will not work because I haven't done this part yet. So how do I evaluate member access? So this function is called evaluateExpr. So I need to evaluate the instance. So this is evaluate the instance. And then the way I'm interpreting this, I need to pass it my variables as well. This is just compiled to JavaScript, so I have some JavaScript magic get property, which will take this object and get a property of this name. So this is my member access. How do I do interpreter for variables? Well, I evaluate the thing on the right, add it to my dictionary of variables, and then evaluate the main thing. So the argument is this assigned thing, and then I call evaluateExpr again, but I'll add this to my map or dictionary of variables. This is my variable name, this is the value, and this is the old variables, and then I evaluate the body. So that's let binding and member access. I'm going to cheat a little bit and copy my code for the call because there's a bit more stuff to write. So if I have a call, then you basically need to evaluate the instance, then evaluate all the arguments, and then invoke the function. And maybe you need to make sure that all your brackets are right. Right, all good. So with this, we should now be able to go back and actually run some of the code I was showing before. So this is an actual picture I took in Rome. So you can see that the Pope loves F#. That's my interpretation at least. And then you can do things like grayscale. And you can already see that when I do things, and you can look at the time as well, my cursor is sort of not moving super fast. So if I say like P is this, that S is, I have another picture here, shadow, and then I can do P. Well, you can see when I'm typing, it's not ideal because it just keeps blocking. And if I add blur, so blur is the very slow operation. Then my screen is blocked. If I change this number to 20, it just hangs for 3 seconds. And if I change this to 6, then I can go and get some coffee. Oh, no, 4.5. So basically, any edit I make means that the whole tree gets recreated. It the interpreter walks over the tree, does all these operations again, and does all the slow blurring again, and that's not great. But at least we've done something. So now the interesting part is, how can we make this better? And this is actually a theme that sort of appears in many normal programming languages as well. So some of the ideas I'll be using here are sort of inspired by how Roslyn, which is the Microsoft new sort of C# compiler, does things. And you would say that C# compiler just takes your program and produces a binary, but it actually does not, because what it is sort of used for as well is when you're editing code in your editor, it parses the code on the fly and gives you all the information that the editor then uses to tell you what's the sort of members available when I type dot, and what are the errors in my program. So this is really something that people have been doing already in compilers that run in the background in some editors and give you hints, and I'm just doing a little bit more. So what it needs to be doing? Well, it needs to cache earlier results, because if I type check a file, for example, and the file doesn't change, then if also the things it depends on don't change, then I don't have to retype check it. And this is something that even the F# compiler does when it runs in the background in your editor, because otherwise it would just not be able to give you any hints in any reasonable time. For doing this, it needs some sort of dependency graph, and I think that's really the important bit, because you need to know what depends on what, and if you make a change, what does get invalidated. And also the fun part is it needs to be able to accept invalid programs, because if I'm in an editor here and I say r dot, then it gives me hints on what members are available, but the program itself is not even valid. This doesn't even parse. So there's the first part, which is the fun part that I'm going to ignore, which is writing parser that can parse programs that are not actually valid. And you can spend lots of time on that and still don't get it quite right. But the sort of easier aspect here is that you need to be able to, in my case, interpret, or in F# case, just type check programs that have some type errors. So if you find a type error, you report it, but then you say, well, maybe the user meant this, and continue assuming this is what they actually meant. So how do we do this? So I'll switch back to my pictures and show you what am I going to do next. So the way this is going to work, and this is actually how the Roslyn does things as well, is that when you edit your program, I'll just reparse it and build the syntax tree, because this is relatively fast. If you had some sort of structured editor where you know what actually changed in the program, then you would just be able to sort of mold the tree maybe. But if you just want a plain text editor and you type any characters in it, then it's really hard to figure out how the tree has changed. So I just don't do that. When you make an edit, you type something, I'll just reparse the tree, because the parsing is the fast part. But then when I want to evaluate it or even type check it, I'm not going to do it by walking over the tree, but instead I'll build a dependency graph, and I'll build a node or an entity for every sort of single syntactic thing. So I'll build an entity for the image, I'll build one for the string, I'll build an entity that represents the result of loading, and this one will depend on the instance, and it will depend on the string. All right. Then I'll build an entity for this P, And here, this is one bit where I'll do something clever, because I know the P is actually the result of the loading, so this P will just depend on this directly. And that's the thing I previously did with these sort of maps for looking up variables. Then I'll build entity for blur and for 5, and for the whole thing. So I produce this green dependency graph, or it's really just a tree in my case. And then I can do evaluation over this. So if I evaluate this thing, this was my image constructor object. This node will have a value pope as a string. This node will be non-blurred pope. Here I just propagate what I've evaluated in the thing I'm depending on. Here I'll get 5, and here will be my blurry pope with a fancy hat. And then this is again just propagating the thing from the previous entity or from the previous node. All right, so we've got this. But then you change the number 5 in the argument of blur. I change it to 7. And what happens is that I get a new tree with new parsed syntax tree. And now comes the clever part, which is that when I start recreating the dependency graph or the tree, I'll actually reuse some of the nodes that I created before. So as I was doing this, I'm actually also creating a cache where I hash, I hash the leaves. So this is string or some constant, and that just gets hashed. And I'll create a dictionary where I can look up entities these green dots based on the sort of syntax that was used to create them, and based also on what they depend on. So if I start doing this, when I have this parse tree, this thing, that's already a node I had before. This thing is a node I had before. And this one is also a node I had before. And also, this one I've had before. And that's it. And for these nodes, I already have their values. So just after I create the dependency tree, without even doing any evaluation, I'll already have values for these. I'll have a value for this. I'll have a value for this. And I'll have a value for this. And this is after I just create the dependency graph. And now comes the sort of new part. So this is where I get to the parts where I have new nodes or new syntactic sort of elements that I didn't create before. So I'll create a new node for 7, a new node for the result of the blurring, and new node for this overall result. So after I parse the program and create the dependency graph, I end up with this. And now if I want to evaluate, get the final result, I know these red things I already have values for, and so I just need to evaluate 7. I need to evaluate the blurring. I changed it from 5 to 7, so this is very blurry pope. And then this is my final result, very blurry pope. But I only actually had to evaluate the value for the new nodes that I didn't see before. So how does this work? Let's get back to the source code. So there's a couple of bits. First bit is that I have this sort of another data structure that represents the dependency graph, and it's sort of very similar to what I had before with just expression trees, except that all these things are now entities. And entity is this structure that has symbol. That's basically the hash of the syntax and the dependencies, and it has a nice mutable value because I'm in F#, we like mutation when it makes sense. So this is a value that I'll set after I evaluate it. And I do still keep sort of, so if I have like binary operator, I still actually know what the syntax leading to it was, but my left and right are just entities in the dependency graph. And then I've got two things. I have this binding operation, which I'll talk about more if we have time, or I can sort of point you to where it is. But what it does is that it takes the syntax tree and it creates this dependency graph, and it does a bunch of clever things here to do the caching. And then I just need to write my evaluator for this version. And the evaluator is, again, just a recursive function that walks over the dependency graph or the dependency tree. And if it evaluates an operator, it will evaluate the left, the right, do the operation to evaluate member access. I'm going to do, so to evaluate member access or method call, I'm just going to recursively evaluate the entity that I depend on, and or the multiple entities that I depend on in this case, and do the JavaScript evaluation I just did before. Now there's a few things where things get different. So if I have a binding, let binding, then to evaluate this, I really just have to evaluate the body, because the argument and the variable, that's already handled by the binding process when I build a dependency graph. So this becomes nice and simple. And equally, when I evaluate a variable reference, I just evaluate the entity that it's actually referring to. So rather than having sort of map with variable to value, I now have variable actually represents some other entity from somewhere else. And I need to do two more things. I need to switch my main code in here to actually use this. So rather than calling evaluate expression, I'm going to call evaluate entity. And the final bit is that this code, there's evaluate entity kind function and evaluate entity. And right now, this is just an alias. But here, this is where I'll do the clever caching part. Because what am I going to do is, I'll say if the value of the entity is none, then I'm going to evaluate it and set the value. So this is where I set the value, and then I'm just going to get the value. So this part is where I do the optimization, where if somewhere in my dependency graph I get to an entity that already has a value, then I just return it and I don't need to evaluate it. So if we switch back here, and I say image load hope PNG, all right, so shadow, this part so far, nothing much happened. But if we start blurring this, let's say 6, well then, for now, this actually didn't do anything. It was 62 milliseconds, because I'm not actually referring to the S thing anywhere in my code. If I start referring to S, then this will be slow, because it's the first time I'm doing the blurring. But then if I say .combine P10, then this took just 400 milliseconds. It didn't have to do the blurring. And if I now vary this number, then it just does the combining operation. So this is the fast part, and I can even be brave enough and put maybe 8 here. So when I do that the first time, maybe that was too brave. No, 6 seconds. But when I then change the number here, it's just the time needed to combine these. So that's the end of the demo, and you can I'll tweet a link to the source code so you can explore how exactly this was done. In summary, so have a look at the Gamma project if you're interested. This was the motivation for this, was sort of making data science easier by taking ideas from spreadsheets and merging them with nice programming language features. And the sort of interesting, geeky part about how this actually works is that I think dependency graphs are really the sort of key thing that you need in these live compilers or live interpreters. And if we do that in a way where we reuse existing nodes, then it makes it possible to do nice caching. And the part that I didn't talk about is writing the parser. I don't know how that can be done. I'm sure there's interesting papers how to write parsers that parse ROM programs, but that's the pain point. So now you hopefully know a little bit more about how to write your own live coding environment. Thanks for coming, and I'll answer a few questions. I see there's one in the back. Thank you.
How do you evict data from the cache? Because if, for instance, somebody typed something like gibberish into your entire AST is broken, you may not have the nodes, or it may not parse to the same tree that you had before. So if you are proactively evicting your data from cache, you will have to recompute it again. If you are saving it for a long time, you may have like terabytes of memory occupied by junk results. How do you handle this?
Yeah, so the question is, how do I remove things from my cache? At this point, because I was just doing it in the browser, and Chrome already takes gigabytes of memory, I just don't delete it and use 1 more gigabyte of memory. But the point is, this is something that you do while you're editing the program. So it's not like when you sort of produce your final program and ship it somewhere, then it's going to cause problems there. So this is really just the sort of developer experience part. And I think if you've used any fancy IDE, they're not the kind of tools that are using your memory very carefully. So it's something I haven't really done in this context, because you just go to a page, you edit your program for sort of a few minutes, and it wasn't pain point that was sort of sufficiently annoying enough for me to have to solve it. But I think you just, well, as the previous speaker mentioned, cache invalidation is one of the computer science problems. So you would probably do the usual things where you remove things if they don't get used for a long time, and you could have some sort of generations in your cache where things that get used twice stay for longer because they're maybe more sensible than things that just get used once. But yeah, the usual tricks would give you decent behavior, I think. Any other questions? There's lunch, so you can always come to me and we can chat later on. Thank you very much for coming.